Okay, guys. So in this platform, we are going to consider, this is a revision that we are going to have on our DC machines, November 2022 exam. So we are going to consider this revision so that we are able to understand how these typical questions are given. So let us consider question number 1, which is 1.1. We are given name 2 characteristics. Take note, these are characteristics of DC machines. As long you are referring to a DC machine, what are the characteristics? Not to consider that it's a generator or it's a motor, just a DC machine. What is it that you need there? All right, so 1, we are going to have the fixed poles in the field winding. Then there is no rotating magnetic flux and also great mass due to heavy wound armature. Then the EMF, as we know that the EMF is actually proportional to the speed and also the flux at the same time, all right? Where we can consider this to be equivalent to a constant times the flux, times the speed times the flux. So that is the relationship that you can consider them. So these are the characteristics of any DC machine that you can consider. All right, so let us move on to 1.2. Can a series motor be started? It's a question. This is a question, all right? Can it be started without some mechanical load? All right, then we are given to substitute, which is to give a reason, like your answer that, like to give a specific reason. Why are you saying yes or no? Okay, so can a series motor be started without some mechanical load? So like I said, this is a question. Can it? We know that this cannot happen, all right? So a series motor cannot. It cannot be started without some mechanical load because at no load, the field flux is too small to allow the build-up of necessary back EMF, which causes the motor to speed up towards infinity until it burns out completely. So we are going to need some mechanical load. In order for this motor to start, we are going to need some mechanical load. That was the consideration of your question then. Then 1.3, it was to explain the term commutating plane. What is a commutating plane? Be sure that you also revise your notes so that it can help you to answer these questions. All right, so the commutating plane is simply the area in which commutating poles have influence. The area in which the commutating poles have influence. That is the commutating plane. It was just the 1 mark for that. So this theory, like I said, just make sure you go through your theory before the examinations and also your calculations at the same time. As we can see, we have got 15 marks on our calculations. Let's see, how are we supposed to obtain these 15 marks? 1.4, we are given the resistance of the armature current of a 250 shunt motor is 0.2 and its full load speed is 1000 revs per minute. Remember, at full load, that is at the initial conditions, at the original conditions. Calculate 1.41. The resistance required in series with the armature to reduce the speed with the full load to reduce the speed at full load, it was 1000. Now it's reduced to 800. The full load armature current is 50 amps. The full load, when it is at full load, that is at original conditions. So this type of a question, as you can see, as you are reading the question, you must understand like the type of question that you're working with. This is a speed control. We're given a speed before at full load. Then after that, they need us to calculate the resistance required in series with the armature to reduce the speed, to reduce the speed. It's a speed control. So the question is, how are we going to answer this question? Remember, I talked about the procedure to solve speed control problems, where you need to read the question carefully, then draw the diagrams that you are going to have according to the information. So the first part, this is the original condition or the initial condition, all right? Where you're given a shunt motor. Remember, your shunt motor, just gonna have a sketch in this case, all right? So let us just have a sketch in this case. So this is a shunt motor. Remember your diagrams, a motor taking or drawing in current. Then we have got the field. So at original condition, you just have your normal shunt motor as it is, all right, with the armature circuit. All right, as we know, this will be the power output on the motor. This will be the input where we have got the input power, but we are not going to worry about that because what we have is not the power. We are given for the input, we are given the voltage, which is 250, then the resistance of 0,2, which is the resistance of the armature. So the resistance of the armature, 0,2, and for the voltage there of 250. So we've got the voltage of 250 volts. The resistance of the armature, we are given this as 0,2 ohms. So this is what we have. And the speed at the full load, which is 1000 revolutions per minute at full load. So like I said, this will be our original condition. So at full load, we are given the speed of 1000 revolutions per minute. Okay, but if you read properly on 1.41, they are saying we are supposed to calculate the resistance that is going to be required, and this resistance must be connected in series with the armature. But this will reduce whatever that is going to reduce. But there they gave us a statement there, the full load armature current, the full load armature current. What is it that we consider at what? At full load. At full load, we are at the initial conditions. At full load, that is where we have the speed of 1000. At full load, that is at original. So this armature current is not for the second or for the final circuit. No, it is for the original circuit at full load. So we also have the armature current there. We are given the armature current at what? At full load. Okay, so there we also have the armature current at full load. I'm just gonna present it here. All right, so remember the armature current is part of the armature circuit that you're given. So this is our armature current at full load, which is 50 amps. So as we do understand our questions of the speed control, as we just do understand these questions of the speed control, that whenever you are given this, whenever you've got this question, you're going to consider the original part as like just current, armature current 1. This will be armature resistance 1, whatever that you're going to have. If you were given the load current, you're going to consider the load current 1, which we do not have in this case. We do not have this load current. We do not have that condition. Anyways, let's see what we have. So the question was, we need the resistance required in series with the armature. So we're going to have this resistance connected to the armature on the final circuit diagram that you're going to have. So on the final condition, there is a resistance connected to the armature. I think we had a similar question of this nature. We had a similar question that we worked with where the resistance was connected in series with the armature. So we're going to have that condition of the final. So let us connect our resistance to the armature. So meaning to say the field is not affected. The field is just going to remain as it is, but the armature, there is a resistance there connected in series, which is to the armature. So you're going to have something of this nature. That is your armature. Remember, does not change. The part of the armature is just going to remain as it is. All right, guys, sorry for that. Just going to have something of this nature. Then this is what we are going to have. We do not know this resistance. All right, this resistance we do not know. We do not know this resistance that we are given. It's just resistance of the unknown, like an additional resistance. Just going to call it Rx. We do not know this, all right? So that is it, guys. Remember the part of the armature, originally there was a resistance of 0.2 of the armature. This resistance of the armature is not going to change. It is just going to remain as it is. But since this is the final diagram, just going to denote everything with a 2, but that does not mean this has changed, all right? Still is the same. And also the input voltage at the supply is not going to change, 250 volts. So as you can see, there's nothing about the field. There's also nothing about the field given there. We do not know the armature current of this final circuit, but there is something that you are given, which is the speed. If you consider here, they are saying the speed which was reduced, all right, with the full load torque to what? It was reduced to 800 revs per minute, meaning to say at the final condition, the speed was being 800. So we are given a speed of 800 revolutions per minute. All right, so this is what we actually have. Like, this is what we have. And with this consideration, I referred that if you are to calculate whatever that you need, like in this case, you need to calculate the final, or the final condition, the resistance that was being extended there, that was connected in series to the armature. We do not have anything about the field. We do not have anything that you're going to consider in a true sense that we said the flux is going to be proportional to the field current. But there's nothing that we're going to consider about the field current in this case. There's nothing that we have. But remember that if we assume that the torque is proportional, if we assume that the torque is proportional to the speed, it follows that we can have our calculations considered from the T1 over T2, which is equal to N1 over N2. In the assumption that the torque is proportional to the what? To the speed, we're just going to have this. At the same sense, if you consider in terms of the EMF, remember, from our ratio E1 over E2 is equal to, we can consider the part of the flux, we can consider the part of the current, so many formulas that you're going to consider here on E. If we consider this, remember the K and the K, I said they'll be equal. And also on this condition, if you take your flux to be equal to flux 2, because in this condition, what you're going to see is that we do not have anything about the field. Remember, the last condition that we had, we ended up taking this flux to be equal to flux 2 because the field current 1 and field current 2 will be equal. So at the end, this flux 1 and flux 2 will cancel. So you're going to just take E1 over E2 is equal to N1 over N2 on a condition like this. So this will be equal to N1 over N2. All right. So this now becomes our speed formula. And remember, from the speed formula, you need to circle what you need to calculate. All right, what is it that we need? We are given speed 1, we are given speed 2. We can calculate the generated EMF 1. We need the generated EMF 2. Why is it that we need E2? Because inside of the E2, that is where Rx is. Remember that your E2, the generated EMF, considering of the final condition. This is the final condition that you have there. So our generated EMF from the specific EMF equation. Remember, it was supposed to be V minus the armature current times the resistance of the armature. Everything that is inside, anything that is considered in the armature. So in this same sense, if you were to consider this, this was going to be considered as E2 is equal to V minus the armature current to then this armature resistance. Now in part of this, part of the armature circuit, you're considering everything that is affecting the armature. There is a series connection of the armature. There is a series connection which is affecting the armature. So you are going to add, because this is in series, so Rx plus the armature resistance. That means this is what you're going to have at the end, because there is a series resistor. So as you can see, we need this in order for us to calculate Rx. But where are we going to have the E2? From the speed formula now, from the speed control formula. That is where we can have E2. So that is why I'm saying we can focus on finding E2. But we do not have E1, which is the generated EMF of the original condition. What was going to be our E1? As we can see, we can calculate E1 in this case. Remember, from our specific EMF equation, that E is equal to V minus I, which is the armature current times the resistance of the armature. So in this case, this is BE1. Then we're going to consider armature current 1. All right. So this is what we have. And this is 1 here. So the part of the armature, there's only the armature resistance there is different from what we have in this case, where there's a series resistance. So in this case, I think everything is perfect. Let us just substitute everything that we have. The voltage at the supply, which is 250, minus the armature current of 50 amps, times the resistance that we are given, which is the resistance of the armature in this case, which is 0.2. So this is what you're going to have. All right. So with this, we were going to obtain the generated EMF, which was going to give us something like 240 volts. So this is 240 volts, which is the generated EMF of the original condition. All right, so like I said, we need this in order for us to obtain E2. We now have this E1, so you can calculate E2. It's either you're going to make E2 the subject or just substitute whatever that you're given in this case. All right, so there, let us calculate. All right, so in this case, you're going to calculate E2. So substituting into the formula, E1 is 240 over E2. This is equal to N1 over N2. So lucky enough, everything this time we are not given a relationship. We are given as it is, the 1000 as it is, the 800 as it is. So remember the previous case, we were given a relationship that N2 is equal to this percentage, a certain percentage of N1, where you need to use a certain relationship. So in this case, it was a straightforward question. You can even make E2 the subject or just solve like this. If you cross multiply, that is E2 times 1000, that's 1000 E2 is equal to 800 times 240. So definitely you are going to divide by 1000 to obtain the value of E2. So that is it. With this, we have got the value of E2, which is the generated EMF of the final circuit, and that was going to give us 192 volts if we simplify this. The purpose of this E2 is that we can use it to calculate Rx. So you see the part of the speed control. We have used the speed. This part is the speed control. This is the formula for speed control. We have used it. Then after that, now we have to consider calculating of Rx. With what we are given, we can calculate our Rx, just a matter of substituting. We now have our E2. So let us substitute and see that is E2 as 192 All right, so we do not have the armature current there. We do not have the armature current too. Okay, let us consider this. The armature current too, we do not have. So what is going to happen with our armature current too in a condition like this one that we are given? All right, if you were to consider, we do not have also the relationship that we are given of the torque. All right, we do not have a relationship that we are given of the torque. Remember, there is that part that you can consider in terms of the torque, like I considered T1 over T2 equal to N1. You can also consider this to be equivalent to the armature current, where you can even use the armature current. Where you can even use the armature current. But in this case, consider to say you do not have the torque. You do not have like a relationship between the torque that you're given. You do not have that. So on a condition like this, you are going to consider your armature current 1 to be equivalent to your armature current 2. So taking this to be equal, we are going to have exactly the value that we were given before. So that is V2, V2, which is of the final, does not change. This is still 250. Our armature current, which is given as 50 amps. So we're going to have 50 amps. Then Rx, we do not know. Then Ra, which is the armature resistance, that is of 0.2. So if we had the relationship between the torque now, then the current was going to be calculated. If there was a relationship between that, all right? So you have to be careful when you're given like this, because we do not have any relationship. So just take the armature current as it is. So we cannot transpose this negative 50 with its bracket, because this is part of the bracket, to the left-hand side. That means on the right-hand side, we are left with the 250. Transpose the 192, it'll be a minus. So that is the condition there. You can even divide by 50 since it's a product. Instead of you expanding the bracket, you can just divide by that 50. So Rx plus 0.2 is equal to the answer that you're going to have if we divide, simplify everything, divide by 50, which was going to be 1.16 ohms. So transposing 0.2 to the right-hand side, that will be a minus 0.2 here. That is, if we subtract 1.16 minus 0.2, that was going to be 0.96 ohms. So there, we are going to take this as our Rx. So as you see, you might have conditions where they are limited. We've got a limited condition. On that condition, you must consider your I1 to be equal to I2. Just use it as it is. But if you consider this condition now, I want you to see this was our 1.41 here. All this part, we were answering 1.41. So we now have our Rx there. All right, from this, just have to consider the way that you're given. But now I want you to see what is happening on 1.42. They are saying what is going to be, what will the motor run, what speed will the motor run if the load torque is halved? If the load is halved, meaning to say that's a half of what we had. Neglect the effect of the armature reaction. There we are given a relationship which is totally different from the original that we had before. Now they are saying the load is up. There is a relationship that you're given there. There is a relationship. All right. So you're going to see that. All right. You're going to see that we are going to have our relationship as usual. So I'm just going to use this part. Remember, we calculated E1, no problem. So let us just have this. Now we have got a relationship which the torque is to be used. The torque is to be used. But this condition is going to also affect a lot of things. All right, let me just remove this so that you see what I'm trying to say there. You calculated Rx, and you might think of what is going to happen with my Rx. This was a condition of 1.41, this condition there. It was a condition of 1.41 where you were given this speed being 8 and this and that. Guys, this time it has changed. It means the second diagram is going to be changed. It's going to be affected. All right. So this is now 1.42. The original second diagram is still as it is. But the final one is the one that is, they're saying on the, what speed would the motor run if the load torque is half? There is a half to the load torque on the final. So meaning to say, we do not have this condition. This was the condition of 1.41 when they're saying calculate the resistance required in series. It was a condition on its own. But this time we do not, there is nothing that we have in this case here. All right. But what happened in this case is the load torque is being halved, meaning to say it's half of what we had before. That means T2 is equal to a half of T1. So T2 is simply 0.5, a half. So they can say it was reduced by 50%, or it was reduced to 50% of the original. So there it is just T1. But on this side, it will be T2 is equal to 0.5 of T1. So remember what we had, the condition of this field part. There's nothing that changed about the field. So there we're just going to go back to that condition of our flux 1 being equal to the flux 2. So the question is, guys, this is the generated EMF of the first circuit of the original condition. So this one is not affected. So that's why I'm not removing this. It is just going to remain as it is. There's nothing that is considered the original condition. The final condition is the one that changed. It is the one that changed. So on 1.42, we have got a new condition. This is the new condition of 1.42. So you're going to calculate the generated EMF, which is already calculated. So there's no need for you to redo this to calculate E1. Your focus is on the final condition. This is where your focus is this time. What is it that we need? What is it that we are being asked? Calculate the speed. What will be the speed? So before the speed was 1,000, now we do not have this. I forgot to remove this because this is of the original condition. The speed there, we do not know this time. So it's a new diagram in its own. It's a new diagram. So we need the speed. So remember what I talked about from our speed control formula. We ended up having our E1 over E2 being equal to N1 over N2 because of the part of the flux being equal. So what is it that we have? What is it that we need? We need to calculate N2, which is the speed of the final. Given N1, the generated EMF A1, we have this. We calculated this before. So we already have this. N1 is already given. So we do not have E2. This is what we need to calculate, E2. So we need to calculate E2. How are we going to have this? We need to calculate E2. All right, first. E2 being the generated EMF of a motor, which does not change. It was going to be equal to, we talked about this, V minus the armature current 2 times the resistance of the armature circuit, which is in this case, there's just a single resistor. We no longer have that additional condition. No, just a single resistor, but we do not have this armature current 2. This time we are not going to take to say, because this is the same. No. We have a relationship of the torque now. I talked about this, that what limited us previously, it was because of this relationship that we are not given of the torque. We are not given this relationship of the torque. Okay, So using the torque this time, we can find the armature current too. How is this possible? How is this possible? Remember, we talked about the torque formula. T1 over T2 is equal to, all right, so they were going to consider field current 1 times armature current 1 over field current 2 times armature current 2, but there's nothing to be considered about the field. So since this armature current is equal, the flux is equal to flux 2, it also follows that the field current on that condition will be equal to field current 2. So this is not there. Just going to consider armature current 1 and armature current 2. So it means, therefore, we're going to consider T1 over T2 is equal to armature current 1 over armature current 2. You need to calculate armature current 2. This is the one that is missing on our formula. Given the relationship between T1 and T2, T1 we do not have, just going to write as T1. But T2, remember, it is given in terms of T1. T2 is equal to what? 0.5 of T1. T1, there's nothing about T1, it's just T1. But T2 is 0.5 of T1. So meaning to say, in place of T2, you're going to write this as 0.5 of T1, which is equal to the armature current 1, which is originally given our armature current 1. Remember, it was 50. So this is going to be 50 over what you need to calculate, which is the armature current 2. So this will definitely cancel. That is a 1 there. So 1 times the armature current 2 cross multiply. That is going to be armature current 2 is equal to 0.5 times 50. So if you multiply 0.5 and 50, that was going to give us 25 amps. So it also follows that since this is being halved, as you can see, the relationship is just straightforward. Our current is also being halved. But anyways, if you didn't realize this, you have to calculate this, okay? You have to calculate this so that you do not mistaken of something that you do not actually understand or that you do not understand. Just leave it like that. Calculate the way that you are used to. Then we can calculate our E2, which is the missing value of our speed control formula. This is what we need there so that we calculate N2. So E2, which is the generated EMF, is equal to V2 minus, which is V2, that is just does not change on the final, that is 250 there. Okay, so this is 250 minus the armature current 225 times the resistance of the armature, which is 0.25. There's nothing that we have, just armature resistance there. There is no other extended part like what we had previously when there was a resistance which was connected in series. This is just as it is now, which is going to be 245 volts. So you have to be careful the way that you're going to consider your questions. So having E2, this was going to help us now to find this N2 from our speed control formula. We ended up having E1 over this. So we're just going to consider our speed control formula here. E1, we have this. We're not going to calculate this because originally E1 was 240 when we calculated. So that's 240 over E2, the one that we just calculated now. Remember, we got 245. So this is equal to N1, the original speed, which is 1,000 revolutions per minute. So that's why we've got 1,000 revolutions per minute over N2. So that was going to give us the speed. If we had to cross multiply 240 times N2, that's 240. N2 is equal to 1,000 multiplies 245. Definitely, you're going to divide by 240. All right, so dividing by 240, we are obtaining the speed, which is N2. And that was going to give us 1,020. So that's 1,020,833 revolutions per minute. Just like originally given our speed in revolutions per minute, it means also our answer is supposed to be in revolutions per minute. So speed control questions, like I said on other questions, they need more revisions. The more questions you attempt, the more you see, okay, this is how they want you to answer these questions. Okay, this is exam answering. How do they want you to answer these questions? Okay, that is what you just need to note and work with that. Okay, so at the end, this is what you're going to have on your final exams, questions like this. So if you know how do they want you to answer these questions, then you are done. All right, so that's 1.42. The speed was going to be our N2 there, which is 1020,833. All right, then we move on to 1.5. A 450 kilowatt. The moment you are given this, a 450 kilowatt, is it a DC generator? Is it a motor? That's the output power. So you're given the output power there, a 450. So that's 450 kilowatt, okay? 380 volts, the voltage being 380 volts, 6 pole, meaning to say the pair poles will be 6/2, which is 3 pairs, remember, the pair poles. The DC generator that you are working with has got a lap connected. So remember, in a lap, C is equal to 2. Then with 180 armature conductors, Z being 180 armature conductors, calculate the number of turns per pole. Okay, so there the question is to calculate the number of turns per pole. All right, so we need the turns per pole, the number of turns per pole. Okay, on which condition for the commutating pole, all right, required for the commutating pole, assuming that the compole ampere turns per pole to be 1,3 times armature amperes. All right, so there we are given a condition of the compoles. All right, so you're going to talk about this part of a compole, which is given the compole ampere turn. So this is actually the compole ampere turn per pole is given to be 1,3 times the armature ampere turn per pole. So it's the armature ampere turn per pole, meaning to say we are talking about the number of turns per pole, which is the ampere turn per pole. We are given that it is 1,3 times. That's the compole that you are given. All right. Then whatever that you're given there, and the brush is to be in a geometric neutral axis. All right. Let us consider this question of the compose. What is it that we need when working with compose? It follows that when working with the compose, it's about the armature ampere turns per pole. That is where it is actually taken from. You are given this, so you're not going to work with cross-magnetizing or demagnetizing. No, we are going to work with the total, which is the one that you're given on your formula sheet. There we are given the formula to calculate the ampere turns per pole, ampere turns per pole. And on our formula, we are seeing that a compole is taken from the ampere turn. Okay, take note, it's ampere turn per pole. So you're going to need this, the ampere turn per pole, which is the total ampere turn per pole. Then now you work with the compose to calculate the turn per each, like just a single turn, like to calculate the number of turns per pole. So there we are calculating the total. Take note of what you're having there. You have got the total of everything. All right, so I'm going to explain about the compole part on its own. Let's talk about this part of calculating the total armature ampere turns per pole. This is for the total. Okay. Our formula is straightforward. So from our formula, we can see that our total That's our total ampere turn. Just gonna write it here, total ampere turn per pole. All right, so this is taken per pole. It is given as 1/2 times the armature current over C times Z over 2P. This is the pair poles, P for the pair poles. We saw this formula and it's a straightforward formula, as we can see. So you just have to figure out what is it that you do not have from the formula. You calculate that. So like I said, we are forced to use the total ampere turn whenever you deal with a compound. The armature current we do not have here. We have this, but we do not have the armature current. So let's think of finding of the armature current. Let's think of finding of the armature current. So there we are just given, it's a 40 kilowatt this DC generator lab connected with this. There is nothing special about this DC generator that we are given. So what we are going to take is we are going to take this as a series consideration, where we understand that in a series consideration, the armature current is equal to the load current. All right, so be careful about that one. Consider it as a series where armature current is equal to the load current. Remember, you need the armature current. But where are we going to have the load current? Remember, there's the power output, and we do understand that the power output is given from the voltage times the load current. So meaning to say, if I divide by the voltage, by the voltage, I'm going to obtain the load current power output over the voltage. So the load current equal to the power output 450 kilowatts. So this is 450 kilowatts, that's times 10 to the exponent of 3 over the voltage of 350. So there we are going to obtain the load current, which was going to be 1,184,211 amps. But like I said, the armature current being equal to the load current of a series, consider this as a series connection. This is just, there's nothing about the shunt that you're going to connect. No. There's nothing there. So your load current is your armature current. So that is going to be 1,184.211 amps. All right, this is our missing value that we need here. So we have got this. So you can calculate the total ampere turn per pole. So the total ampere turn per pole is 1/2 times the armature current, 1184,211 over C. Remember, it's a wave where we are given this as a 2 times the Z, 180 the number of conductors, over 2 times the pair poles. How many pair poles? 3. So this was going to give us 2,960,528 ampere turn per pole. But this is the total, like the total ampere turn per pole is the total that you're dealing with here. This is the total. Now let's go back to the compole, the part of the compole condition that we are given there. All right. There's a compole that we are given that the compole ampere turn per pole, 1,3 times ampere turn per pole. That's the condition. All right, so let's take our condition of the compole. Let me just rewrite this so that you understand me. It's just gonna have this. So it follows that for a compole condition, we are given a condition there, like we are given 1,3 times the armature turns. 1,3 times the armature turns. Okay. So this follows that the total that we are given, what is the total? Is the total ampere turn, this one, is the one that you are going to need now in order for us to calculate the ampere turn, because this is the like total ampere turn. But there's a compole that they are saying, okay, for a compole, we are given a condition there. 1,3 times the armature, the total, which is the total actual. Guys, let's go back. I talked about this here. 1,3 times, that is the product to the armature ampere per pole. So we calculated this, all right? 1,3 times 2960,528, which is ampere 10. So we were going to obtain this one, 3848,686, which is ampere 10 per pole. This is when the condition of the compole is given. The condition of the compole is given. So we now have what we refer to as the ampere 10 per pole, the total ampere 10 per pole. So how do I calculate the armature current from this? The armature current, which is the one that connects these two, it is given as the ampere 10 per pole, which is the total ampere 10 per pole over the 10 per pole, which is ampere 10. Just like how many tens per pole over the 10 per pole. So as we need this one, the 10 per pole, this is our question. Our question is to calculate the number of tens per pole required. The number of tens per pole. So this is what you consider here. That's the number of tens per pole. So in order for you to have this, which is the 10 per pole or the number of tens per pole, you cross multiply, then you divide. So it is going to be total of that ampere 10 per pole that you calculated from a compole over what? Over the armature current. So you divide to the armature current. So this is from a compole. That is what you have to consider there. So with this total, which is the one that we calculated before, our total was 3,800 actually. So you're just going to take this as it is 48,686 divided to the armature current. Are we having the armature current? We have this armature current. Remember, we used this armature current in calculating of this here. The armature current is not going to change. 1184,211. That was our given armature current, the one that we calculated before. So this was going to give us 3,250 to 3 decimal places, which is just going to 3,25. That is tens per pole. The number of tens per pole, which is the 10 per pole. So this is how you answer typical questions whenever you are given a compole of this nature. They are going to give you a condition. Is it 1,3 times? Is it? So you use your formula, which is the total ampere 10 per pole from your formula sheet. Then you use this is the condition now of the compole. There's a condition that you're given that the compole is 1,3 times of the armature 10 per current that you're given, the armature ampere tens per pole. That armature ampere tens per pole, it is the total, which is the one that you calculated from your formula, which is from this formula. You calculate this. You use the condition that you are given to calculate now the total that you have when a compole is considered. Then using this formula of the armature current, or just straightforward to the tens per pole, it is equal to the total armature, which is from the compole now. The total armature ampere tens over the armature current. With this formula, you can calculate the tens per pole, the number of tens per pole that you're given, like what you're given in this condition. So this is how we can attempt these typical questions. So like I said, your DC machines, speed control, everything that you have on a DC machines, it's all about more questions that you do, more questions that you work with, the more that you actually understand, okay, to say, this is just one and the same as the question that I did in this question. It'll be just like a repetition. So more to come from Mason African Motives till we meet again.